So that homework assignment analyzed diatomic molecules from the first period of the periodic table with molecular orbital theory. Wasn't very hard because the only orbital that exists in the outer shell of a first row element is the 1s. Today we're going to move on to the second row in the periodic table, and we're going to try to analyze the bonding in diatomic molecules that are in the second row using molecular orbital theory. But this will be a little trickier because now the valence orbitals that exist for atoms in the second row of the periodic table are now the 2s, the 2px, the 2py, and the 2pz, because if you're in the second row on the periodic table, your outer shell is the second energy level, and the second energy level has two sublevels. So we're going to see one atom in its valence shell having a 2s orbital, a 2px, a 2py, and a 2pz, trying to bond to another atom in the second row on the periodic table, which has a 2s, a 2px, a 2py, and a 2pz. And as they approach each other, we're going to have to see how those 8 atomic orbitals, does that make sense? There's 4 on the first atom, 4 on the second. How those 8 atomic orbitals merge together to make 8 molecular orbitals. And that's where we're going to wind up going today. And we're going to try to draw a molecular orbital energy level diagram for any diatomic molecule made up of atoms from the second row on the periodic table. So we're going to have the valence atomic orbitals on the first atom, and in terms of energies, the 2s is the most stable, and the 2p's are all degenerate, with another atom of the same element from the second row on the periodic table, with its valence orbitals, the 2s, and then the 2px, 2py, and 2pz. So we're going to look and see how these 8 atomic orbitals merge together into 8 molecular orbitals. And we're going to take them a pair at a time. We're going to start with the 2s's. Now, you know the shape of a 2s orbital, it's spherical, right? So if the 2s orbitals merge together, the analysis is going to be exactly the same as what we talked about for the 1s's last week, because they're spherical as well. You can add them directly with the same wave function sign to create a bonding orbital, or you can combine them with different wave function signs to make an anti-bonding molecular orbital. What are they going to look like? Look back to question number 1 on the last homework assignment. It's going to look exactly like the bonding and anti-bonding orbitals you created. That'll live in infamy now, Mr. DiFilippo. So we're going to try to figure out what molecular orbitals are formed here. And the first ones we're going to do are going to be the 2s's. And when the 2s's on 2 different atoms combine together, they're going to look exactly like the sigma bonding we created earlier and the sigma anti-bonding we created earlier. Only now they're going to be made from second energy level orbitals. So we're just going to adjust their name. See if this makes sense to you. The 2s atomic orbitals combine exactly the same way as 2 1s atomic orbitals do. But the names of these new molecular orbitals will be sigma 2s bonding and then sigma 2s anti-bonding. Now, the more interesting analysis is what's going to happen with the p orbitals. How is the 2px, 2py, and 2pz orbital on one atom going to merge together with a 2px, 2py, and 2pz orbital on the other atom? Because that's going to be a giant mess. Well, what we're going to do is we're going to take them a pair at a time. Just like we took the 2s and the 2s, I'm going to look at this and go, how do the 2px and the 2px's merge together to form a pair of molecular orbitals? How do the 2py's merge together to form a pair of molecular orbitals? And how do the 2pz's merge together to form a pair of molecular orbitals? Now, before we do this, you have to recognize the geometry of these orbitals, because the 2px orbitals are distinctly different in their geometries relative to the 2pz's and the 2py's. How could you describe how the 2px's are related to each other spatially? What are they doing to each other? Just how they look. If they're going to overlap, they're going to overlap by what? Pointing directly at each other. Does that make sense? So if orbitals overlap by pointing directly at each other, what type of molecular orbitals do they form? What do you think? If orbitals point directly at each other and overlap, they form molecular orbitals that have what symmetry?
Linear.
So what's that name if you have linear symmetry?
SP.
You're giving me a hybridization. No, you're thinking of something different. That would be if you have two different bonds. If you have a 1s orbital and it overlaps with an sp3 and they point at each other, what type of molecular orbital, what type of bond do you get?
Oh.
Anybody else help out? Oh, I didn't want to do that yet. Back.
Sigma 2p.
So you're going to get a sigma bond.
Yeah.
Sigma bonds or sigma orbitals are the ones that are formed when atomic orbitals directly point at each other. So the 2px's, because they're pointing at each other, are going to form molecular orbitals that are called sigma. All right, can you see that? Now look at the 2pz's. Are those pointing at each other? Those are not going to form sigma molecular orbitals. What do you think those are going to form?
Pi.
And how do you think, what kind of molecular orbitals do you think the 2py's are going to form?
Pi.
Those are parallel as well. They're just like the 2pz's. Does that make sense?
Mm-hmm.
So if you can sort of see that ahead of time, that'll actually be sort of helpful. So good. So here we go. We're going to take the 2pz's first, okay? So we're going to take each pair of p orbitals and we're going to combine them by adding their wave functions or by subtracting their wave functions to make a bonding MO and an anti-bonding MO. And we're going to start with the 2px's because they're a little bit different than the others. They're actually directly pointing at each other, which we tried to point out in the homework today. If the orbitals point at each other, when they combine to make a bond or a molecular orbital, that's going to be perfectly symmetrical around the inner nuclear axis. And so it's going to be considered a sigma bond or a sigma molecular orbital. So here's how the 2px's are related in space. So if we try to combine them where the wave functions are the same, and anytime you have an orbital with multiple lobes, each lobe has its own unique wave function sign. This will be positive, and this has to be the opposite, negative. If this is positive, this has to be negative. So when you have multiple lobes, each lobe, the wave function sign changes as you go from one to the other. If we want to add these together, we have to make sure the two lobes that are overlapping have the same wave function sign. So I'm going to make the central wave function signs be positive. So now when those central lobes overlap, they're going to add their probability together. The amplitude of the electron wave increases, and you'll have a region of high electron probability in the middle like this. Look at that really dark region there. High electron probability here. So that's going to attract the two nuclei. That creates a bonding molecular orbital. Its sigma symmetry to its name is sigma. It came from the 2px's, and it's a bonding. So sigma 2px bonding is the name of that molecular orbital. So when you add the 2px's, they create this bonding orbital. When you subtract the 2px's, they'll create an anti-bonding orbital. And the way you subtract them is by having them overlap with wave functions that are opposite in sign. So I'll have one of the inner wave functions lobes be positive, the other one be negative. And that's a crest and a trough in the ocean overlapping. They cancel out probability. So when those two lobes overlap with each other, they cancel out the ability of the electron being found in that position. And you wind up getting a big hole right in the middle of the orbital. That's going to be an anti-bonding orbital. The name of that, it's still sigma symmetry because it's still perfectly symmetrical around the inner nuclear axis. It's called sigma 2px anti-bonding. And this is how the 2p orbitals on the x-axis combine to make a bonding and anti-bonding molecular orbital. Now let's go to the more interesting ones, the ones that are parallel to each other. Let's go to the 2pz's. So the 2pz's are parallel, and if the atoms approach each other, these will actually overlap a little bit on the top and a little bit on the bottom. If we want to add their wave functions, we have to make sure that the top lobe has the same wave function sign and the bottom lobes have the same wave function sign. So if you overlap some positive wave function with some positive wave function, you get constructive interference. It increases the probability. And although it may not have necessarily been obvious, if you increase a negative wave function sign with a negative wave function sign, they add together as well. And anytime they overlap, they will increase the electron probability. So by combining the pz orbitals in this fashion, we will get two regions of really high electron probability between the nuclei. The nuclei are here and here. Now there's nothing right here, but this region right here is between the two nuclei. And this highly probable region is between the two nuclei. So this will cause the two atoms to bond together. That'll be a bonding molecular orbital. But its symmetry is different now because it's only going to look the same if you rotate it 180 degrees. So it is no longer a sigma molecular orbital. We've now created our first pi molecular orbital. It's an orbital that is completely symmetrical, rather it's an orbital that is only symmetrical upon a 180-degree rotation around the internuclear axis. So the name of this orbital would be the pi 2pz bonding. And then if you have two atomic orbitals, they can always combine two different ways, one by adding wave functions, one by subtracting. So the other orbital you're going to create from them is going to be if the wave function signs are opposite. So notice I have positive and negative are going to overlap at the top, and negative and positive are going to overlap at the bottom. And when they overlap, they cancel out electron probability, and you're going to wind up having a big hole right in the middle of the two as they cancel out their probability like this. That would be an anti-bonding orbital. Now, it's still pi symmetry. It's only going to look the same if you rotate it 180 degrees. So this would be called a pi 2pz anti-bonding molecular orbital. So these are the two molecular orbitals that the 2pz's create. The 2pz's are on the z-axes. They're the ones flat on the paper. The 2py's are perpendicular to that, but they're parallel to each other as well. So when the 2py's combine together, they're going to form the exact same looking molecular orbitals I have here, only they're going to be rotated 90 degrees. So I'm not going to draw pictures for that again, but they're going to come out exactly the same. So the two 2py atomic orbitals will combine the same way as the two 2pz atomic orbitals do, exactly the same, forming pi molecular orbitals. They'll form a pi 2py bonding and then a pi 2py anti-bonding. So these pi orbitals, the pi 2py bonding, the pi 2pz bonding, are identical. It's just they're rotated 90 degrees. So when we draw our molecular orbital energy level diagram, you're going to see that the pi 2py bonding and the pi 2pz bonding are the same in terms of energy. We call them degenerate. Similarly, the pi 2py antibonding and the pi 2pz antibonding are identical. They're just rotated 90 degrees. So they're going to have the same energy. So you're going to see them listed at the same energy step level in our molecular orbital energy level diagram. They're considered degenerate also. So now that we actually know what each of the 8 new molecular orbitals are going to look like, let's see if we can now rank them in terms of energy and draw a molecular orbital energy level diagram. The energies you see here are going to be determined experimentally, and we're not going to go through how they determine the exact energy of the orbitals. Although it's in the reading, I would actually like you to go through and know how we determine that what the energies are for each of the different molecular orbitals. But once you've done that, then we're going to essentially just get to the point where I want you to be able to draw a molecular orbital energy level diagram for a diatomic molecule for atoms in the second row on the periodic table. So it's an energy diagram. We label the y-axis with energy, and we're going to draw the valence atomic orbitals for the 2 atoms on the left and the right. And now the atoms are from the second row on the periodic table, so their outer shell is no longer the 1s. Their outer shell is the second energy level, which would consist of a 2s orbital and a 2px and a 2py and a 2pz. And at the beginning of this, we said we're going to draw molecular orbital energy level diagrams for diatomic homonuclear molecules from the second row. Homo means the same, so that means the 2 atoms have to be the same element, either 2 nitrogens or 2 oxygens or whatever they are, the same element. That just means that the 2s and 2p orbitals for each atom in the diatomic molecule will be the exact same energies, because every single oxygen atom, their orbitals have the same energy. Every single nitrogen atom, their orbitals have the same energy. So as long as the 2 atoms are the same element, then the energy level of all the 2s's would be the same. The energy levels of the 2p's would be the same. So right now you see that these 2 atoms have 4 + 4, 8 atomic orbitals. If these 2 atoms bond together, those 8 atomic orbitals will metamorphosize into 8 molecular orbitals, and they're the 8 molecular orbitals we've just talked about. So let's write those orbitals in now. First, the 2s's combine to form a sigma 2s bonding and a sigma 2s antibonding. The sigma 2s bonding is the lower orbital energy. The sigma 2s antibonding is the higher. These two orbitals will always be lower than the molecular orbitals that come from the 2p's. So these are the first two orbitals ever to fill in a diatomic molecule. With the 2p orbitals, we first talked about the 2px's, how they'll form a sigma 2px bonding and a sigma 2px antibonding. So the sigma 2px bonding is the lower orbital, and the sigma 2px antibonding is the higher orbital. Then we saw the 2py's and the 2pz's actually form pi molecular orbitals. And because the pi 2py bonding and pi 2pz bonding are the same orbital, just rotated 90 degrees, they're degenerate. Their energy levels will be the same. The pi 2py antibonding and the pi 2pz antibonding orbitals are exactly the same. They're just rotated 90 degrees, so they'll be the same energy. So you notice I've got pairs of orbitals here that are low, pairs of orbitals that are high, and that's because of the similarity between those two different molecular orbitals. So on the bottom, we have the pi 2pz bonding, identical in energy to the pi 2py bonding. And on the top, we have the pi 2pz antibonding, identical in energy to the pi 2py antibonding. Okay? And these energies from lowest to highest are what we've determined experimentally. So we believe this is the pattern in which the orbital energies go in a diatomic molecule for atoms in the second period. You will need to know that pattern. Okay? And just like on the homework for today, you were doing molecular orbital energy level diagrams for atoms from the first row. Next homework assignment on Wednesday, you're going to be doing molecular orbital energy level diagrams for atoms in the second row on the periodic table. So you're going to need to know this pattern. So we're going to do a couple of examples. If we want to try to analyze the bonding in diatomic carbon using molecular orbital theory, we're going to need to write that molecular orbital energy level diagram, and you already have it, so you can maybe just fill in the electrons for that if you want. You try to predict how two carbon atoms bond together with Lewis theory, and you go carbon dash carbon and try to put in all the electrons till you get to 8. The only way you can make an octet is if you make the two carbon atoms have a quadruple bond, which means it would be the strongest bond in the history of chemistry. And we actually create diatomic carbon molecules. It is not the strongest bond in the history of chemistry. It's more equivalent to the strength of a double bond. So Lewis theory is unable to predict how a diatomic carbon molecule can form, but molecular orbital theory can. If we try to draw a molecular orbital energy level diagram for diatomic carbon, and you have this drawn, you've got the s and p orbitals for one atom on one side, that'll be the first carbon atom, and the s and p orbitals for the other carbon on the other side. And we know that it doesn't matter what the elements are, when atoms from the second period bond together, they're going to form a pair of molecular orbitals from the 2s's. They'll form a pair of molecular orbitals from the 2px's. And they'll also form a pair of molecular orbitals from the 2py's and from the 2pz's. These are a little bit different. These are pi molecular orbitals. So you wind up having a pattern that looks like this. Now, how can we use this to predict properties of the diatomic carbon? Well, just like before in your last homework assignment, you're now going to put the number of valence electrons for the two individual atoms in the atomic orbitals on the left and the right. And from carbon's position on the periodic table, you should know that carbon atoms have 4 valence electrons. So for the first carbon atom, I'll put its 4 valence electrons. And for the next carbon atom, you put 4 valence electrons. When the molecule forms, those outer 8 atomic orbitals metamorphosize into the 8 molecular orbitals in the middle. And so those 8 valence electrons now have to go into these orbitals. And just like you go into a concert, you always pick the best seat available. So as those electrons try to scramble for where they're going to go, the first 2 electrons will go here. And the next 2 electrons will go here, right? Those are all the best seats. That's the first and second row in the stadium. The next 2 electrons will go into the pi 2pz, pi 2py bonding orbitals. But remember, because electrons are negatively charged, they would spread out like this first to minimize repulsion. So electrons 5 and 6 would go like that. And then finally, the last 2 electrons would pair up here. So according to molecular orbital theory, these are the orbitals in which electrons would be occupied. Now, what can we predict from that? Well, if you notice, a number of these electron pairs are in bonding orbitals. How do I know it's a bonding orbital? Because it says B right there, right? There's a B, there's a B, there's a B. And some of the electrons are in anti-bonding orbitals. I've colored them in red, right? How do I know that? Because it's a star. That's an anti-bonding orbital. So if you can identify how many bonding and how many anti-bonding electrons there are, you can figure out the bond order. It's bonding electrons minus anti-bonding electrons divided by 2. 6 green electrons minus 2 red electrons divided by 2. And this would predict that a diatomic carbon would have a bond order of 2, which, oh my gosh, exactly matches experimental data for diatomic carbon molecules. So molecular orbital theory can predict the correct type of bonding for diatomic carbon, whereas Lewis theory was unable to do so. Now, this particular molecule has all of its electrons paired up. So Mr. DiFilippo would now know that means it's diamagnetic. And if you want to write the electron configuration notation for this, we're going to read all the filled orbitals from bottom to top. So here we go. What's at the bottom? Sigma 2s bonding, 2. Then what's next? Sigma 2s antibonding, 2. And then what's next? We have that level that has 2 different orbitals in it. So we're going to combine those and just call that the pi 2p bonding sublevel. We'll leave the z and the y off. We'll say pi 2p bonding 4, and that would be the electron configuration notation for a diatomic carbon. Mr. DiFilippo, question.
Yeah, so where did you get the 6 from for the bond order? I'm confused.
Counted up all the green electrons because those are the electrons in the bonding orbitals. Every bonding orbital has a name with a little b in it, right? That's how you know it's bonding.
Yeah.
And the anti-bonding ones are the orbitals with a little star above it, or the asterisks.
Oh. Okay.
Make sense?
Yeah.
So if it does, Mr. DiFilippo, you and everybody else, let's see if you can do the exact same thing for diatomic fluorine. I'll give you like 3 minutes. I want you to see if you can draw a molecular orbital energy level diagram for diatomic fluorine. And then just like diatomic carbon, tell me its bond order. Tell me if it's paramagnetic or diamagnetic, and then give me its electron configuration notation. So take a few minutes and let's see if you can do it.
Do you mind going back on the other slide? I missed the electron configuration. Thank you. Okay.
So to draw the molecular orbital energy level diagram for the diatomic fluorine, you would draw the atomic orbitals for one fluorine atom on the left side. You would draw the atomic orbitals for the other fluorine atom on the right side. Fluorine atoms have a total of 7 valence electrons each, and those 7 and 7, 14 electrons will eventually go into the newly created molecular orbitals when the atoms bond. So what are those molecular orbitals? You should have the sigma 2s bonding, the sigma 2s antibonding. The 2px's form the sigma 2px bonding and the sigma 2px antibonding. And then the py's and the pz's form the pi orbitals, the pi 2pz bonding, pi 2py bonding, then pi 2pz antibonding, pi 2py antibonding. So the original 7 electrons for each fluorine should be written on the left and the right side, representing the valence electrons for each of those unbonded atoms. Then when the 2 atoms bond together, those atomic orbitals metamorphosize into the molecular orbitals, and the 14 electrons now have to fall into the most stable molecular orbitals. So you've got to put 14 electrons into the molecular orbitals. 2 go into the bottom one, 3, 4 would go here, 5, 6 would go here, 7, 8, 9, 10, 11, 12, 13, 14. There's our 14 electrons. Now, to analyze the bonding in the molecule, you have to identify which one of the electrons are found in bonding molecular orbitals. I've colored those in green. You'd have to identify what electrons are in anti-bonding orbitals. I've colored those in red. That allows you to calculate the bond order. It's bonding electrons minus anti-bonding electrons divided by 2, and that should come out a bond order of 1. This would predict a diatomic fluorine would have a single bond. All the electrons are found in pairs in the molecules. There are no unpaired electrons. Therefore, this would be a diamagnetic molecule. And its electron configuration notation, you're going to have to read each of the sublevels from bottom to the top. So here we go. Starting from the bottom, sigma 2s bonding 2, then sigma 2s antibonding 2. Then the next level is just called pi 2p bonding 4, then sigma 2p bonding 2, and then finally pi 2p antibonding 4. Okay. Any questions on completing a molecular orbital energy level diagram for a diatomic molecule from the second period?
So the superscripts indicate the amount of electrons in each orbital.
Just like if you're going to write the electron configuration for a nitrogen atom, you would go 1s2, 2s2, 2p3. What do those superscripts mean? How many electrons are in those sublevels? This is the exact same thing.
Okay, got it.
And you get 14 electrons because fluorine is diatomic.
And each fluorine atom from its column on the periodic table has 7 valence electrons.
Oh.
Right?
Mm-hmm.
So for these 2 different molecules you just analyzed, we've determined that the bond order for diatomic carbon was 2 and the bond order for diatomic fluorine was 1. So which one of these molecules has the highest bond energy?
The fluorine.
So fluorine has a single bond holding the 2 atoms together, and the carbon has a double bond. So which one's going to take more energy to break apart? It's probably going to be the one with a higher bond order, more electrons attracting the nuclei. So actually it'd be the diatomic carbon, if that makes sense. What would be the longest bond length?
Fluorine.
The fluorine.
Yeah, so remembering this just from Lewis theory, same principles apply. If you have a higher bond order, the atoms will be pulled closer together. So the diatomic carbon would have the shorter bond length. So the diatomic fluorine would have the longer bond length. Exactly correct. So you can answer similar questions about bond energy and bond length once you've determined bond orders from molecular orbital theory. Now, the molecules we've been discussing are atoms of the same element that are diatomic, C2, F2. What I want to do is I want to do one other example showing a diatomic molecule where the atoms are from different elements. We call those heteronuclear molecules, and just show you the slight difference here in how your molecular orbital energy level diagram would look. When you have atoms of different elements have different numbers of protons in their nucleus. And the more protons you have, the stronger they can attract their valence electrons. That means the valence electrons undergoing more attraction will have lower energy. So when you're drawing an energy diagram, the valence orbital energies for atoms that have more protons are going to be slightly lower because of the greater attraction. So if we take a molecule like CN, carbon and nitrogen have different numbers of protons in their nucleus. Nitrogen actually has one more proton. That extra proton in the nitrogen nuclei will attract nitrogen's 1s, 2s, and 2p orbitals more strongly, making their orbital energies a little bit lower. So nitrogen's greater nuclear charge will make its atomic energies lower than carbon's. So here's how the molecular orbital energy level diagram would look slightly different. We still have two atoms from the second row in the periodic table. So I'm going to put the carbon orbitals on one side, the nitrogens on the other, and their orbitals are going to be the 2s, the 2px, the 2py, the 2pz, same second row of the periodic table. But now when I do the nitrogen, because nitrogen has one more proton, I don't want to write the 2p orbitals exactly at the same energy level. I don't want to write the 2s orbital exactly at the same energy level because nitrogen has an extra proton. Its orbitals are going to be slightly lower in energy because they'll be a little bit more stable because they have a little bit more attraction. When you take your test next week, I'm going to take my ruler out. I'm going to hold my ruler up and see, are you putting those nitrogen orbitals a little bit lower than the carbon orbitals because they need to be a little bit lower because of the extra proton in the nucleus. Now, besides that, there's no difference. You're still going to create the exact same molecular orbitals we talked about before. The two s's will combine to form a sigma 2s bonding and a sigma 2s antibonding. The 2px's will combine to form a sigma 2px bonding and a sigma 2px antibonding. And the py's and the pz's will form the pi bonding and the pi antibonding just like before. So the molecular orbitals look the same, but they are based upon slightly different energies of the atomic orbitals on the left and the right. If this makes sense to you, why don't you take 2 minutes, fill out this molecular orbital energy level diagram for the carbon nitrogen diatomic molecule, and then answer the same questions. Give me the bond order, tell me whether it's paramagnetic or diamagnetic, and then write out its electron configuration notation. And then in 2 minutes, we'll show you the answer and see if you're able to do that. All carbon atoms have 4 valence electrons. All nitrogen atoms have 5 valence electrons. So in this diatomic molecule, you're going to have 4 plus 5, 9 valence electrons. I've placed them in the molecular orbitals from most stable to least stable. The electrons I've colored in green are in the bonding molecular orbitals, and the ones that are signified in red are in the anti-bonding orbitals. So this should allow you to calculate the bond order for a CN bond. It's 7 bonding electrons minus 2 anti-bonding divided by 2 gives you a bond order of 2.5. Because there's one unpaired electron up there in the sigma 2px bonding orbital, that one electron spinning by itself creates a magnetic field. Therefore, this substance is going to wind up being paramagnetic. And the electron configuration notation, reading it from bottom to top, is sigma 2s bonding 2, sigma 2s antibonding 2, pi 2p bonding 4, and then sigma 2p bonding 1. Any questions on creating these molecular orbital energy level diagrams for diatomic molecules in the second period instead of the first period? You'll have an extra homework assignment tomorrow where you'll still be working on first period elements, and then the homework for Wednesday and Thursday will be on second period elements. So the final thing we want to talk about concerning molecular orbital theory is that it actually can be used to explain something we don't have a good explanation for, and that's the electron arrangement in molecules that possess resonance. We can't draw a Lewis structure for a molecule that possesses resonance. We have to draw 2 or 3 structures and say, imagine the average of that. And that's not really very satisfying. We want to be able to say exactly where all the electrons are located. And molecular orbital theory will allow us to do that. We're going to do 2 examples to finish up today. The first example is going to be based upon the most common molecule known that has the property of resonance. It's an organic molecule, a hydrocarbon called benzene. I would like you to know benzene is C6H6, and I would like you to know its structure. In this case, the carbon atoms are not arranged in a 6-membered chain, but it's hooked in a circle. It's called a ring. So the 6 carbons are bonded in a 6-member ring, and each of those carbons have 1 hydrogen bonded to it. If you're told that and you try to draw the correct Lewis structure for that by the correct number of total valence electrons and trying to make octets for the carbons, you'll wind up having a ring in which the carbons alternate single and double bonds around the ring. And this is actually the Lewis structure for the benzene molecule. The ring has a double bond, single bond, double bond, single bond, double bond, single bond. If this were the only structure for benzene, then we would have bonds in the molecule like this one, which are short, because right, a double bond pulls the atoms close together, and then bonds that are long, then short, then long, then short, then long. But X-ray diffraction analysis of a benzene shows that the bond lengths are not short, long, short, long, short, long. They're all the same. This is not the true representation for a benzene molecule. And in fact, it shouldn't have been. If you think about it, you can make it a proper Lewis structure for benzene by alternating the positions of the single bonds and double bonds. So therefore, there's a different resonance structure you can draw as well, which would be this. Now all the single bonds and double bonds have been moved to their opposite spots, which means if you focus in on any one bond in the ring, let's take the one on the left, it's a single bond in this structure, a double bond in this structure, the bond order of that bond should therefore be 1.5. And every single bond in the ring would have a bond order of 1.5, which means all the bonds should have the same lengths, which is what we find experimentally. So benzene we consider is a resonance hybrid of these 2 resonance structures with every single bond in the ring having a bond order of 1.5. Okay, so in the ring, the carbon-carbon bond order, 1.5. Let's even see how it's doing this. Now, each of the carbons have a steric number of 3. If that's the case, what's the hybridization of every single carbon in the benzene molecule? So Ms. Gilman says sp2, and that's correct. Steric number 3 makes sp2 hybridization. The sp2 orbitals are trigonal planar. Look at this carbon here. Look at that arrangement. That's perfectly trigonal planar. Trigonal planar. trigonal planar. So I actually have all these drawn properly, which means I can draw every carbon and hydrogen flat on my paper, which means the entire benzene molecule is actually a flat molecule. So each carbon is sp2. And as it turns out, because they're all sp2 and those sp2 orbitals are trigonal planar, the entire benzene molecule is a planar molecule. It's flat. Now, if you have sp2 hybridization, you will have one p orbital left over that is not hybridized. And if you remember where that exists, if the sp2 orbitals are flat on the paper, that p orbital is perpendicular to them. It's got to be pointing out towards you and going back behind the plane of the paper. So every carbon in this ring has a p orbital that's perpendicular to the plane of the paper itself. And I want to make sure we can see that. So I'm going to draw a little picture of our benzene ring. And then I'm going to tilt the ring up so we can look above and below the plane and see if we can see those p orbitals sticking above and sticking below. So here's my benzene ring, and I'm looking straight down at it. If I lift the bottom of the ring up like this, you should be able to see the p orbitals extending above and below each of the carbons in the 6-member ring. Okay? So this is how the p orbitals are arranged in the benzene molecule. Now, what do each of the resonance structures indicate? There's a double bond, then a single bond, then a double bond, then a single bond, then a double bond, and a single bond. Well, a double bond is a sigma bond, which is the blue, plus a pi bond, which is the overlap of a pair of p orbitals. So one resonance structure is just making distinct pi bonds between pairs of carbons. Resonance structures assume these p orbitals make distinct pi bonds, maybe like this. The bottom two on the left are making a pi bond, the bottom two on the right a pi bond, and the back one is making a pi bond. Those are the double bonds, and then the other ones not double bonded just have single bonds. But if we have the other resonance structure is just assuming that different sets of p orbitals are making the pi bonds. So right now it looks like only every other pair of carbons has both a sigma and pi bond. And in the other resonance structure, you're just saying that different sets of carbon atoms make pi bonds and different sets of carbon atoms don't have pi bonds. These are what the two resonance structures indicate, and neither of them are correct because we think the real molecule is the average of those two. How can that be happening? Well, remember when we started talking about molecular orbital theory last week, the very first thing we said was that molecular orbital theory went on the assumption that the molecular orbitals are created can be under the influence of all the atoms in the molecule, not just pairs of atoms. So molecular orbital theory would say if you have these 6 different p orbitals here, they're not going to just interact in little pairs, they're going to all interact with each other. So instead what's happening is all these p orbitals are all merging together to make one giant pi bond. So molecular orbital theory predicts that the 6 2p atomic orbitals do not make 3 distinct localized pi bonds where the electrons are localized between pairs of carbons. It says they actually all combine together to make one big pi bond. Now, how should I draw that? I should draw that like this. All the p orbitals overlap with each other, and you get a big ring of electron probability above the benzene ring and an entire circle of electron probability below. That causes all of the carbon-carbon bonds to be bonded together a little bit more tightly, and they all get increased in their strength by the same amount. Okay? Now, there's one false statement you've written down here. It has to do with this letter or this word right here, okay? Because that's really not true. The 6 2p atomic orbitals do not all combine together to make one big pi bond. If you're starting with 6 atomic orbitals, how many molecular orbitals do you have to make?
6.
So this is not really just one big molecular orbitals created. It's really a system of 6 molecular orbitals, but I'm not going to draw each of them individually, but they all encompass all 6 atoms is really the key. So really, because 6 2p atomic orbitals are combining, they're really making 6 molecular orbitals, not just one big molecular orbital. So please understand that, because I did slightly state that wrong, but I'm trying to just simplify it a bit for us. So that big ring of those 6p orbitals all merged together is really a combination of 6 molecular orbitals. So we don't call it one big pi bond. We want to give it a name to indicate that it's a one big collection of many pi bonds or many pi orbitals. So we call it a pi system. And because the electrons are spread out over multiple atoms, we call it a delocalized pi system. So a delocalized pi system is a group of pi molecular orbitals which are spread out over more than 2 atoms. And my picture up here is 6 pi molecular orbitals in which the electrons are spread out over 6 atoms. And what these electrons do is they migrate around the 6 atoms. They strengthen every single bond in the ring. And they actually add an extra half a bond order to every bond. So we get a 1.5 bond order for every carbon-carbon bond in the ring. Okay? We believe this happens in every molecule that possesses resonance. You form delocalized pi systems. So if you have any molecule you've drawn resonance structures for in your entire life, those molecules all must have delocalized pi systems. And what do they have to have geometrically to have a delocalized pi system? You see this right here, that p orbital? How's it related to this p orbital? How's it related to this p orbital? How's it related to this p orbital? How are those related geometrically?
They're linear.
Linear means they're pointing at each other, I think. So I would use a different term. Because they're actually not pointing at each other. What's the word you can use to describe them? It starts with P.
Parallel.
Parallel, right? Those p orbitals are parallel to each other. So molecules possessing resonance always bond with delocalized pi systems, and they are always formed from parallel p orbitals every single time. Now, benzene's a complex molecule. It exists as a ring. Things that we've seen that have resonance are things like ozone, carbonate ion, nitrate ion. Let's try one example of those. I want to show you what the delocalized pi system looks like for those. So let's finish with a nitrate ion. We've drawn its Lewis structure before. Nitrate is an ion that possesses the property of resonance because when you draw the skeletal structure, you fill in all the electrons till you get to the maximum number you're supposed to have, which is 24. You don't get an octet for the nitrogen. So we're going to have to move a lone pair into a sharing position and make a double bond so that everything has an octet. When you do that, we made a double bond with the right O, but you would go, oh my gosh, I could have made a double bond to the left O, or I could have made a double bond to the bottom O. So this molecule possesses resonance, and you would have to draw all 3 of these with double-headed arrows between them to represent the bonding in the nitrate ion, because you can't draw a Lewis structure for the nitrate ion. Well, what's really happening? What's happening is every single atom that can participate in a double bond, which would always be the nitrogen, but here the right O, here the left O, or here the bottom O, so essentially every atom needs to have a p orbital in its outer shell, and they all have to be parallel. So we're going to try to draw this. Now, what's going to be the hybridization of the nitrogen?
SP3.
Good try. 3 bonded atoms, sp2.
Oh, SP2, yeah.
How about the right oxygen? What's its hybridization?
sp2.
sp2 as well. What does the left oxygen look like its hybridization is?
sp3.
It can't be, though, because you need to have a p orbital in its outer shell so that over here it can make a double bond. So you see it's not sp3, it's got to be sp2. This one looks sp3, but it can't be if in one of the resonance structures it's going to make a double bond. So if any atom is ever going to be making a double bond in one of the resonance structures, you need a p orbital in its outer shell. So even though it may look sp3 on paper, remember, these really aren't the correct structures. It has to be sp2. So all atoms that can form a double bond in at least one resonance structure must have parallel p orbitals to form the delocalized pi system. And the only way you can do that is if you leave a p orbital unhybridized. You can never be sp3. It can always be sp2. So one way to figure that out is to look at a particular atom in all three structures, and whichever structure gives you the lowest hybridization, that would be this one, it's sp2. What's the lowest hybridization for this oxygen? Oh, it's in this one, sp2. What's the lowest hybridization for the right oxygen? Is from this one, sp2, then you'll have it right. So here's what the ion actually looks like. The nitrogen in the center is sp2 hybridized. I draw its 3 sp2 orbitals, trigonal planar. It has a p orbital sticking above and below. So if you're going to have resonance, that means all of the oxygens that can make a double bond with the nitrogen have to have p orbitals that are parallel to the nitrogen's p orbital. They have to look like this. So on a piece of paper, you make sure you can draw things parallel. Okay, they got to look like they're parallel. If they all have p orbitals, they're all sp2 hybridized as well, so they have to be trigonal planar. So you could fill in the trigonal planar geometry of this O, and then do your best to make the trigonal planar of the O's that are not flat on the paper. That kind of looks kind of good like that to me. Okay, so now all those p orbitals on the outside are able to overlap with the p orbital on the center. Here's how the delocalized pi system works. It goes like this. The outer O's merge with the central nitrogen, and the electrons flow through all of those p orbitals, making every single bond a little bit stronger. In stick figure mode, here's my nitrogen atom with its sp2 hybridization. Here's the 3 oxygens on it. If it's going to be resonance and every O can make a double bond in at least one of the resonance structures, every O has to have a p orbital parallel to the central nitrogens. So you've got to draw their p orbitals up and down like this. And then they all bond to the central nitrogen. So you draw a dotted line from each outer O to the central O on the top, and you do the same thing on the bottom. Here's the remaining sp2 hybridized orbitals on each of the O's, and here's your delocalized pi system. It looks like a big propeller or something. That's actually what the pi systems look like. So these bonds here, which are the sigma bonds between the N's and the O's, are sigma sp2 plus sp2. The pi bonds, because it's actually a combination of 4 different pi orbitals, we're not going to give their exact names. I'm just going to call this whole system up here delocalized pi system. And that's how you draw the bond orbital model for something that possesses resonance. You actually show you have a pi system where the orbitals are not localized between pairs of atoms. They're delocalized amongst many different atoms, okay? And the biggest mistake people make is they think that the oxygen p orbitals overlap with each other. They don't. The oxygens don't overlap with each other. They're too far apart. They only overlap with the nitrogen's p orbital. So you don't do this. Okay, that doesn't exist. They're too far apart. They bond like this. Okay.